Welcome back to the discussion of spatial networks. In previous few videos, we looked at the motivation for spatial networks in terms of location-based queries in urban areas where transportation networks and roadmap constrained our day-to-day movement. Then we went under the hood. We looked at conceptual data models including entity relationship diagrams as well as graphs. We also looked at logical data models, particularly query languages, how we added new statements like connect with and with recursive to query graphs for connectivity or shortest path. Now we are going to go even closer to the computer platform in the terms of physical data model and look at data structures and algorithms. Okay. So this particular video will focus on data structures, and after this particular video we should be able to list at least a couple of common data structures representing graphs in main memory. We should also be familiar with couple of file structures which represent graphs on disks and possibly compare them. Okay. So again, here is the big picture. Remember, we talked about conceptual data models such as graphs and entity relationship diagrams, logical data model query languages, and now we are really going into physical data model very close to implementation and performance. And the goal is to look at storage structure. Next video will come back and look at algorithms. Okay. So without further ado, let's look at a simple graph which is shown on the bottom left. And if you remember, there are 5 nodes, 1, 2, 3, 4 and 5, and there are 6 edges. So for example, node 1, from there we can go to 2, from 2 we can go to 3 and so on. Okay. So if we were to represent this in main memory using simple data structures, there are 2 common representations. The first is based on matrices, and you may have come across matrices also in mathematics, and in this case we need to define rows and columns. So for this particular graph, a simple representation uses nodes for both rows and for columns. So here is a matrix which has 5 columns, 1 per node, and 5 rows, 1 per node. Okay. To represent edges, we can use matrix entries. So if you think about this entry 1, this may represent an edge from node 1 to 2. So this edge 1 to 2 is represented as matrix entry in first row, second column. Okay. More abstractly, if we look at an entry in row A and column B, this will be 1 only if we have an edge from node A to node B. Okay. If it is 0, means there is no edge. Okay. So using this, we can represent the information, and you can also query. If I want to know all the edges that are going out of a node, then we could look for a particular row. So for example, first row shows me all the edges going out of node 1. Okay. If I want to know about all the edges which are incident, which are incoming to a particular node, we'll look at columns. So for example, first column shows you all the edges which are coming into node 1. So in other words, there is only one edge from 5 to 1 that is incident on 1. Okay. And once you have this representation, you can use matrix algorithms. So if you remember some of your matrix operations, such as matrix multiplication, we can perform that repeatedly, again and again and again to get connectivity kind of information. Now in computer science, there is another very common representation which is based on adjacency list. So if you have programmed references or pointers in languages like Java, C++ or C, people often use that kind of a representation to make a adjacency list data structure, and which may look like this. So here you notice the list is a list of nodes. So all 5 nodes are in a list. Maybe node 1 is first, node 2 is second, and so on. And then with each of these nodes, we attach a list of successive nodes. Okay. In other words, if let's say you are standing at node 1, there are 2 outgoing edges to node 4 and 2. So 4 and 2 are successors, and they are listed in just after 1 to represent the 2 edges, the edge from node 1 to 2 and the edge from 1 to 4. This kind of data structure is often again useful to find out all the successors or predecessors of a particular node. Okay. In this case, successors are easier, predecessor is a little bit harder, but you can do that. Okay, good. So this is the life in main memory, and many of you may have taken other computer science courses or done programming and written code in Java and so on, where you use this data structures. Okay. When you go to disk, the story changes a little bit. On disk, we often think in terms of tables and in terms of disk blocks. Okay. So, let us first look at a tabular representation of this graph. In the traditional relational databases, people often use normalized tables, okay, where each cell is an atomic value. And if we were to adhere to that kind of a representation, we will need two tables. We may have a table for nodes and another table for edges. The node table may have node ID as well as more node properties such as location. The edge table again may have the start node, end node for the edge, and then edge length or other properties. Okay. Now, oftentimes the shortest path algorithms are run in a specialized environments outside databases, and they prefer a denormalized representation. And in this case, we actually merge the two tables into one, because we know that oftentimes when we are at a node in a graph, we often want a list of all successor nodes. Okay. So, this other representation looks very similar to the adjacency list we just saw in main memory. So, here notice that in this particular table there are 5 rows, 1 per node, and for each node we have listed the successor nodes as well as predecessors. And this table is often preferred over the normalized version for shortest path queries or other graph queries. Okay. There is another challenge on the disk environment, and that is why instead of using the word data structures, people sometimes use the word file structures when we refer to storage on disk. And this challenge is to essentially partition your file across disk blocks. Many of you know that the unit of access on disk is not in terms of words, but it is in terms of disk blocks, which may be kilobytes. So, in other words, even if you need the successor of one node, that may represent only, let us say, 100 bytes, but the disk will send you a kilobyte anyway, right? So, you will do a lot more work. So, you might as well then group the records which are likely to be accessed together in the common disk pages. Okay. So, this is a central problem when you store data on disk. Okay. So, in case of graph, we can show you two ways to divide up a graph into disk pages and try to see how we can rank them. So, let us suppose we have a different graph here with 16 nodes and then some of these edges. Okay. So, and these nodes are embedded in a geometric space. So, you can think of latitude and longitude or xy coordinates. Okay. So, how should we divide it up into disk pages? And let us for simplicity assume that each disk page can hold 4 nodes. Okay. You can divide it geometrically, which is shown in the second figure. So, here all the red 4 nodes go to one page, green 4 go to other, blue 4 go to other, and so on. And it is called geometric partitioning because you have taken a vertical line and a horizontal line to cut up the graph into 4 pages. And incidentally, this is the dominant way to deal with data in spatial databases. If you think of R tree, quad tree, grid file, they all think like that. Okay. Now, one of the insights in this space is to say that really another partitioning may be more suitable, which does not follow geometry, but instead it looks at the graph edges and try to cut as few edges as possible, as shown here. So, notice here the green nodes are together, red nodes are together, brown are together, and you do not have a very strict kind of geometric partitioning. But what is being done is you notice these yellow edges, and they are the ones which go across the disk pages, and we are trying to reduce them. So, in this case you see that the cut edges are 1, 2, 3, 4 and 5, whereas the geometric one had many more, it had 7. Okay. So, one of the insight is that graph computations, they often access information by connectivity, that is edges, and if all edges are equally likely to be accessed, then you would prefer min-cut graph partitioning. If there is a non-uniform distribution, then you may prefer partitioning, which minimize the sum of weights on cut edges. Okay. To give you a more bigger picture, here is a road map, major roads on Minneapolis, and we are showing you 2 ways to partition it across disk blocks. And in this case, the white edges are showing you the cut edges. Okay. So, you may want to pause the video here for a second or two and stare at these pictures and check which between the left and right, which one has less white. Okay. And that is the one which has fewer cut edges, and that is the one which will reduce disk I/O for graph queries. Right. And in this case, hopefully we will agree that on the right side you have fewer white, and that will be preferred. Great. So, the last activity in this module is a small exercise. So, let us look at this simple network which we have seen before in terms of query languages and so on, and this has 6 nodes and few more edges. And we'd like you to consider different ways to partition this network across disk pages and rank these partitionings by the cut edges. Okay, so suppose you could partition it like this. So nodes 1, 2 and 3, these are together and you may cut these edges, right? Or you might have 2, 3, 4 together. So which are these 2, 3, 4 and you might cut these edges and so on. So you may consider these partitionings, count the number of edges cut and suggest which is most preferred to reduce I/O cost. Okay. To wrap up this video, we looked at main memory data structures and disk-based file structures for storing roadmaps and other spatial networks. And one of the insight was that we should minimize the edges cut by disk partitioning to reduce I/O cost. Okay. In the next video, we'll come back and look at graph algorithms and which may use these data structures to answer connectivity or shortest path query. So look forward to seeing you then.